start off with plate tectonics. I'm going to start writing some things down here and in preparation. So the word tectonics comes from the Greek for movement and deformation. So we'll say movement and deformation of Earth's crust. And more than the crust is moving, but since we live up here, that's what we study, the outer reaches of Earth. If we could take another step here, we're going to look at the three fundamental layers of Earth. So these layers are basically density stratified. In other words, they're based on their mass over volume. So one of the questions I often ask is, what is density? And density is a measure of mass over volume. And usually the units we use are either are grams per centimeters cube, right? Grams per cc, you've probably heard. Now, if we look at a simple model for the Earth, we'll find that we do a little pie chart here showing, like if we're going from the center of the Earth here to the crust of the Earth, right, a little wedge through the Earth, we find that the outermost, thinnest layer of the Earth is called the crust, right? There's a crust. And then about 2,900 kilometers down, we'll put 2,900 here, we have a region here called the mantle. And the mantle by far is the most voluminous part of the planet. Your book says 80%, so 80% by volume. It's a little bit more than that, but 80% is a good number there. You'll find the crust is very little. It's going to be less than 1% by volume. Now, as we go deeper down, there is a core, but the core is divided into this outer liquid core and an inner solid core. We'll put inner solid. And so this would be the core. And so going back to this idea of density stratified, the crust, well, in fact, the crust, there's a couple of types. There's oceanic crust, and there's continental crust. And for ocean, we're looking at about 3 grams per centimeter cube. Continental crust is a little bit less dense, even though it's thicker, but it is less dense. It's about 2.7 grams per centimeter cubed. And then the mantle varies quite a bit. It goes from about 3.3 grams per centimeter cube to about 5.7 as you go deeper down. So there is a trend going from 3.3 to 5.7 as you go deeper down. And the core can vary anywhere from about 10 grams per centimeter cube to, in the inner core, 13 grams per centimeter cube. So there you go. You see that layering. Remember, stratification means layers here. So the layering is based on density, right? The next question is, how do we know that the outer core is liquid, and how do we know, in fact, the core is 2,900 kilometers deep? All right, the other number I want to put down here is the radius of Earth, 6,400 kilometers. So if you measured from the core out to the surface here, it'd be about 6,400 kilometers. Another number to add there. Now, we know this composition, or at least the nature of the core, based on seismic waves. So remember, seismic waves are earthquake waves, right? These are due to earthquakes. And the two that we're concerned with here are called body waves. We'll look at the first set called body waves. The others are called surface waves. We'll talk about those when we do earthquakes. But the body waves, they originate at the focus. Originate at the focus. And the focus is basically the point at depth where the earthquake occurs. And these two body waves that will form, one will be the P wave, which is also called the primary. And then there's the S wave, which is the secondary. And they both travel a little bit differently. The P wave will travel by compression and dilation. And probably the best way to show a P wave is using one of these springs or this toy called a slinky. And so I can show you how I can show a wave going across here. There it is right there. And so that's the compression and dilation. You'll see the springs compress and dilate. That's a P wave. And one thing we should add about the P wave is that P waves travel through both solids and liquids. P waves travel through solids and liquids. The analogy I make when you're swimming in the pool, you're doing the crawl stroke. If you are wearing webbed gloves, you can compress more water molecules behind your hand and propel yourself through the water. So fluids are compressible, and obviously solids are as well. Now for S waves, one thing that S waves do, they have a shear motion. And this shear motion basically is sort of a side-by-side wiggling motion. So if we had energy going in this direction, the particles would wiggle like if you were wiggling a rope, right? And one thing that we know is that solids may be sheared, but liquids cannot. And the reason why they cannot is because molecules in a liquid are not attached to each other. They slip by, so that you cannot shear them because the molecules will slip right by. There's literally no strength in a liquid in the shear direction, right? So the key thing is that the S waves now do not travel through liquids. All right, so now we're going to use that information about seismic waves to tell us something about the outer core being liquid. So let's draw a little model of the Earth over here. And in this model, we're gonna show an earthquake here. So that would be the focus. And we'll find that when seismic waves occur, they radiate out in all directions, right? They'll radiate out in all directions. Usually geologists, instead of showing the circles, we're going to show these vectors. So, and whenever you show a vector, know that there's always wave fronts perpendicular to them, right? So what I'm showing here, let's say these are the P waves in the black color here. And so these P waves, they travel through the Earth. They kind of bend a little bit as they go deeper in the Earth because they encounter rock of a stronger density. But one thing we do see is P waves do travel entirely through the Earth. They do go through the Earth, which means they're moving through the Earth. Now, if we look at S waves, right, for the S waves, they'll do the same thing. They'll go out to the surface, and they'll radiate out in all directions. In fact, let's put a couple more in here. But the ones that travel straight down toward the core through Earth disappear, or they stop. They just stop. They do not penetrate the core, which means that there must be something here preventing them from traveling to the Earth. And that must be that liquid outer core, right? That liquid outer core. In fact, there's a zone out here that we call the S wave shadow zone. S wave shadow zone, or just S wave shadow. One of the questions I ask on the quiz or the exam is, what does the S wave shadow tell us, right? And there's two pieces of information. The first thing it tells us that we have a liquid outer core. The second thing it tells us is it gives us an idea of the size of the core. That's how we know the outer core is liquid.